So we'll continue our discussion on optical sources that we started before the minor. So we had discussed LEDs, and starting today we'll discuss lasers, or semiconductor lasers. Sometimes also known as injection lasers, or laser diodes, or sometimes diode lasers. Okay, so you might see all these different names for basically the same thing. Okay, so basically with LEDs, right, we saw that the emission was sort of broadband and incoherent. Okay, so there basically the light was generated due to spontaneous emission. Okay, so basically we were sort of injecting carriers, so electrons in the conduction band and holes in the valence band, and they were sort of just spontaneously recombining to emit photons. So basically there was no relationship between different recombination events, right? They were all sort of independent, and each recombination event sort of generated a photon which was traveling in a random direction, and the frequency also could be slightly different, right? So we saw that the bandwidth was pretty broad, right? Whereas for lasers, as you know, basically we go into the regime of what is known as stimulated emission, right? So basically what's happening now is you set up sort of this medium for light emission now inside an optical cavity which provides feedback, and you inject enough carriers such that what you have now is population inversion, right? And basically what happens is that basically a photon within this laser cavity can stimulate a recombination event, right, and generate another photon to be emitted which is identical to this incident photon, right? And so you can see that basically if this process happens with many carriers and happens many times over, you can see that you get lots of photons with the same frequency and the same propagation direction. So you'll get a bright coherent beam with a well-defined frequency and a well-defined direction of emission, unlike the LED. Right, so population inversion, as you know, like if you talk about any system, right, so let's say you would have two levels, right? So typically what happens is most of your atoms which can absorb photons, right, are in what is known as the ground state, right? So basically, if you have an incident photon, the probability that it will be absorbed to excite an atom to the excited state is much higher, right, than the probability that if you have some few atoms here, that it will stimulate an atom down and emit, right? So if you have more atoms here, then the probability is basically the probability of absorption or emission goes as, the probability of absorption will go as the number of atoms in the ground state, the probability of emission will go as the number of atoms in the excited state. And typically in thermal equilibrium, you have more atoms in the ground state, so that's why you have predominantly absorption, right? But if you could achieve a condition where you have more atoms now in the excited state than in the ground state, right? So this is known as population inversion. So you inverted the population so that there are more atoms in the excited state and less in the ground state. So now you can see that if you have an incident photon or light coming in, then the probability of it causing another emission event is higher because now there are more atoms in the excited state, so it can stimulate an atom down to the ground state, and the probability for absorption is lower because there are very few atoms in the ground state. Okay, so Under such conditions, you can see that basically the light will experience gain, right? Because the emission probability is higher than the absorption probability. So basically, the you can see the light will experience gain. So that's the operative principle to make an optical amplifier or a laser, right? Is to have some gain medium, and you achieve the gain by having population inversion. Right, so there are some tricks that one has to play typically to get this population inversion. Right, you can't, for example, get it in a two-level system. You have to have another third level or four levels sometimes that are used in typical lasers to get this population inversion. In semiconductor lasers, as you know, that basically how we are getting this sort of population in the ground and excited state is just by current injection, right? So you can see, so basically the emission probability here will depend on the number of electrons here, versus, and the absorption will depend on the number of electrons here in the valence band, right? So basically what you need to do is deplete the valence band here, so you create a lot of holes here, right? Such that you don't have any electrons to absorb, or very few electrons to absorb the incoming photon, and primarily the incoming photon will cause an emission, right? So in the semiconductor laser case, it means that you have more electrons in the conduction band or close to the conduction band edge than the number of electrons close to the valence band, right? So that you can imagine. So remember how we construct these devices. We have p-n junctions, right? So you have some p material here which gives you a density of holes, and then you join it with some n material, right? So if you have a very large doping, then mostly you will have holes here, very few electrons, right? And so you can imagine that if you inject a reasonable amount of current, you can exceed the few number of electrons here already by some current injection here, and you can achieve population inversion, right? So we'll see that. So the difference between LEDs and lasers is that one is doping in lasers is very high, right? To achieve this large carrier concentration, basically to get population inversion, right? So the doping in lasers is typically 1 to 2 orders of magnitude, or maybe even 3 orders of magnitude higher than LEDs. So typical doping for LEDs maybe is 10 to the 16, 10 to the 17 per cubic centimeter. For lasers, it goes up to maybe 10 to the 19 per cubic centimeter. Okay, so basically, so yeah, I hope you understand what population inversion is, and right, another thing that is done to achieve this population inversion or high carrier concentration is to make the device smaller, right? To make sort of the region in which the carriers are concentrated to be smaller, such that again, for the same amount of current, you get a very large carrier concentration. Right, so like typically, so the construction sort of basically is the same, right? So you have like a p-n layer and then an active region in between, just like the LEDs, right? So you have this double heterojunction to enhance the light emission, right? So the active region has a slightly smaller band gap than the p and n regions. But now the device dimensions typically, so the width of the device here typically is like 5 to 15 microns, okay? And the length of the device, so here into the board, is about let's say 200 to 500 microns, somewhere there, okay? So for the LED, typically this W is also much bigger, okay? So for the LED, typically W is also, let's say, up to 100 microns or so. But for laser, basically, we shrunk one dimension to be very narrow compared to the other, okay? And so that's the first thing to be done. So then now for the same amount of current, now the active region volume is smaller. So that means for the same injected current, the carrier concentration here is higher. Also, we increase the doping here, right? That also increases the carrier concentration. So both these effects help you to achieve population inversion. And then, yeah, so this active region width is also made extremely small. So typically, let's say 100 nanometer. Right, so let's say it could be 100 to 300 nanometers somewhere there. For LEDs, this could be up to maybe up to a micron. Okay, so now you can see that basically, so we also discussed that this will also form some sort of waveguide, right? And basically the waveguide mode will look somewhat like this, and it will propagate into the board like along the length of the device, and then come out of the device like this. And the mode will look slightly elliptical, right? Because there is more confinement in the vertical direction because of this index contrast. Whereas in the horizontal direction, the only confinement is from the width of the device, right? So the mode coming out typically of these lasers is not circular, okay, but slightly elliptical. So when this goes out and diffracts into the far field, it becomes elliptical in the other direction, right? You know that diffraction basically, the smaller dimension diffracts faster, right, than the bigger dimension. So it becomes elliptical in the other direction in the far field. Anyway, so because this mode is elliptical, and you know that in an optical fiber the mode is circular, right? So basically you need some cylindrical optics after this, some cylindrical lenses or something to make the mode circular for efficient coupling into the fiber. Right, and the emission here now is preferentially in this direction along the length of the cavity. Okay, for LEDs we saw that the emission was sort of random across all different angles, and then we basically were able to collect a very small fraction of the total light emitted. But here basically because of the stimulated emission, the light emission is very directional, right? And all the photons which are emitted are sort of emitted in the same direction they are coming out like this. Right, so basically these things also, okay, so one more thing that is done is to make this optical cavity, right, which is basically to circulate these photons. So you have these photons being emitted, so this optical cavity makes them circulate within the cavity many times, so they cause many stimulated emission events, right, before leaking out of the cavity. So basically, how to do that in the device is basically so these two facets at the front and at the back, right? So those facets are first of all made atomically flat, okay? So that's a process known as cleaving. Okay, so basically cut this facet such that it's atomically flat. Okay? So that automatically gives you a nice mirror already, because remember the refractive index inside the device is pretty high, like 3.4 or something, and outside, let's say, it's air. So you have a huge reflection just from the refractive index contrast. So that already gives you a very good or decent cavity. But you can make the cavity even better by having some high reflection coating. Right, so you make some coating here, multi-layer coating, such that you get a very high reflectivity, let's say 99% or something, at the wavelength of emission, or the wavelength that you want to make your laser. Right, so you can also coat these facets with some high reflective coatings. But anyway, so the most basic laser would just be a cleaved facet, right? And if you want to enhance the efficiency further, then you can make high reflectivity coatings. So basically what all this does is that it boosts the optical power coming out, right? So for LEDs, we saw that let's say at tens of milliamperes of current, the optical power coming out was, let's say, of the order of 100 microwatts. Okay, so for lasers, for the same amount of current here, you boost up the output power to almost 10 milliwatts. Okay, so you increase the output power by roughly 2 orders of magnitude, and mostly, so we'll see that is coming from the enhancement in the internal and the external quantum efficiency, right? That we discussed for LEDs, that's pretty low, especially the external quantum efficiency. But here you can see, because the emission is directed, right? Almost all the light comes out. There is no light lost or trapped within the device. So the power is very high. And then the line width. So for LEDs, we saw that so this line width was like 10 terahertz or something, right? So the bandwidth in wavelength was, let's say, 50 to 100 nanometer, in that range for the infrared range, right? For lasers, now we can make the line width really small. So typically you can easily go down below gigahertz line width. Okay, so in terms of line width here, you can very easily go below a nanometer without much effort at all, and then you can even go down to almost single frequency. So basically line width less than megahertz by again doing some tricks that we'll see. So that basically so the spectrum coming out is almost just a single frequency. Okay, so already we see, so in terms of applications for communication, right? So we get much more power. The bandwidth is much narrower, right? So much more power helps us, of course, going longer distances for the same loss. Much narrower line width also helps us going longer distances because the dispersion is much smaller, right? And then we also get much higher modulation bandwidths. Okay, so for LEDs, we saw that if you modulate the current, the maximum bandwidth, data bandwidth that we can go is, let's say, like you can't go much beyond 200 megahertz. With lasers, you can go easily up to almost 10 gigahertz. Okay, so in terms of data rate, also you can go much higher. Okay, so if you look at this device from the side here, right? So basically, you have this active region here where the light emission is taking place, right? And these two facets are the acting as mirrors, right? Right, and you have current injection into the device, which is creating population inversion and gain. Right, so you have this gain medium within this cavity of length L. Right, so basically, if you look at the electric field, so and then you have some optical mode which has a profile something like this, right? Because of the refractive index contrast between the active region and the P and N regions, right? And this mode is like now traveling in this waveguide form back and forth, right? And then eventually power coming out. So if you look at the electric field associated with this optical mode, so that experiences some gain, right, on propagation within this waveguide or laser cavity. Okay, so we can write the evolution of the field as some gain factor G here, right? So this G denotes the gain factor for the power, right? So you know that the optical power is goes as mod d square. So if you look at how the power varies, so that will look like this. Right, so you can see that there is some exponential gain factor, which is basically coming from this population inversion. Okay, so this G gain factor here will depend on basically the number of carriers that we inject into the active region. Okay, so this gain factor here. Okay, so first of all, this gain factor is a function of frequency. So it's a function of lambda or omega. Okay, and it's also a function of the carrier concentration. Omega and lambda are the same thing. Okay, so typically if you look at the peak gain that is happening, that goes with the carrier concentration as, so it scales linearly with the carrier concentration. So you can see here the units of G are per centimeter or per length, right? So the units of G are per length. So for example, here you can write the power like that, right? Exponentially gain. So units of G are per length, right? So this is typically per centimeter, denoted in per centimeter, right? This is carrier concentration in the active region. So this is per centimeter cube. Okay, so this is N is the carrier concentration in the active region, right? It depends on the current, right? And this NT is some constant, which is known as the transparency concentration, right? So basically, you can see that if N is lower than NT, then G is negative, which means you don't have gain, you have loss. Right? So as you increase the current, at some point you reach N equal to NT, which is the threshold for population inversion. Right? And once you increase the current further and you go beyond NT, then G becomes positive, and you have population inversion and gain. Okay, so this NT depends on the material, right, and the doping, etc. So you can see from here, the units of this proportionality constant here has to be centimeter square, right? Because this is per centimeter cube. So this has units of area. Okay, so this sigma G is known as the cross section. Okay, so this is known as the gain cross section because it has units of cross sectional area. Okay, or sometimes also known as differential gain coefficient. Okay, so that's also a material property, right? Of course, you want a high value of sigma G so that you get larger gain for the same carrier concentration on the same time. Right, so for example, if I take the typical material system that we work with for sources used at telecom wavelengths, right? Indium gallium arsenide phosphide. So for this material system, typically this transparency concentration is somewhere around 10 to the 18. And this differential gain cross section is 10 to the minus 16 centimeters square. Okay. So that gives you an idea of the numbers involved here, right? So you can see, so this, you need to exceed this carrier concentration, right? So you can see that typically we go into U10 to the 18th or 10 to the 19th. Right, so if I look at this gain cross, like this gain coefficient G, okay. So of course it's a function of frequency or equivalently photon energy. Okay, so for example, so we are plotting the photon energy in EV, right? So you know the wavelength of emission is 1.24 divided by this number, right, in micron. And then we plot G in per centimeter. So 0 denotes basically transparency, right? Or beyond which you achieve population inversion. Right, so it's loss below here and then gain above here. Okay, so as we change the carrier concentration N here, this gain keeps increasing. So okay, so these are for different values of N or different values of current, basically. Right. So at very low currents, so this is N like 10 to the 18. Right, the G value is negative everywhere, so you have only loss, right? And then I start increasing the current and N goes beyond NT. Okay, so this is for 1.2 times 10 to the 18, 1.4, 1.6, and this is 1.8 times 10 to the 18. So you can see that now I get gain over some range of frequency wavelengths. Okay, and as I increase the current, the peak gain, right? So if I look at where the peak gain is, that is, so the peak gain value is increasing, of course, and also this peak gain is shifting towards longer wavelengths. Shorter wavelengths or higher frequencies, right? And also the gain bandwidth is increasing with increasing current. Okay, so if I look at this, so if I just take the peak for each curve, right? So that gives me this peak gain value GP. So if I plot the peak gain value as a function of the carrier concentration in the active region, that typically goes like this. Okay, so it's not exactly linear, this relationship here, but once you go sort of sufficiently beyond NT, it's well approximated by a linear function. Okay, so this dotted line shows this linear dependence here with N. Okay, and this intercept here would be NT, right? At which the gain is 0. Okay, so this shows the linear relationship here, and so it works well once you go sufficiently beyond NT. Okay, so I mean, if you want to know this exact curve here, this goes something like log of some n over n naught. Okay, where this n naught and nt are related like this. Okay. Right, so you can basically imagine so what's happening, right? So as we increase the current injected into the device, I'm creating more and or I'm injecting more and more carriers into the active region here, which increases the radiative recombination rate and the stimulated emission going on, right? And basically which is resulting in higher and higher G, right? So first of all, I increase the current such that I reach transparency, which is G equal to 0. So for low currents, you're below population inversion, which means absorption is dominant. So you're having net loss, right? So that is n less than nt. So at n equal to nt, you just create equal population in ground and excited states. So now your G is 0. And then beyond that, you're in population inversion region, right? So basically, as you know, lasing action happens once the gain, so if you look at, for example, the round trip gain here, compensates for the internal losses happening, right? So here we've just considered the absorption by the of photons and emission of photons by the carriers, right? But there are other things going on. So for example, the photons emitted can be lost through some internal scattering here, right? They could leak out through the mirrors, right? So there are other loss mechanisms, right? And one, basically what you want is to increase this G such that it compensates for all those other losses, right? And when the round trip gain becomes equal to the round trip loss, then you reach this threshold, right? Beyond which basically you get a very strong light output. So you can imagine that sort of up until this threshold current, the device is mostly operating like an LED, right? Where basically your stimulated emission is still not sort of dominant over your other losses, and basically the light coming out is just randomly emitted spontaneous emission events. And then once you cross this threshold, stimulated emission has become dominant, and all the photons coming out have the same frequency, same direction of propagation. Okay, so yeah, and so you can see that just like in any other laser, there is a particular gain bandwidth, so range of frequencies over which you get gain, and the value of the gain is also frequency dependent. Okay, so now if we again go back to this picture, right, and you want to know about so where this threshold occurs, threshold for lasing, right? So let's say, for example, if you have cleaved facets here, right? So there is some reflectivity here. These are acting as some mirrors, right? So you have some reflectivity R1 here and R2 here, right? So if it's just cleaved facets, for example, this reflectivity would just be, so if the refractive index inside is n, outside is a, then this is just, you know, n minus 1 by n plus 1 square. Right? That's the reflection coefficient for normal incidence. So you can see, for example, if you put n equal to 3.4 or 3.5 here, you get about 30%. This comes out to be about 30%. So if you don't do anything more and just have clean facets here, then you get about 30% reflectivity mirrors, which sounds very bad, right? But the gain values are so large, so you can see here that you're talking about gain coefficients of 100, 200 per centimeter, right? And remember, this is coming in the exponent, right? So we are talking about really large gain values. Even so, the length here is, let's say, a couple hundred microns, right? So even for such a short length, we are talking about really large gain values. Okay. So even with such poor mirror or such poor looking mirror reflectivity, you can actually make a laser out. I mean, if you know something about some other kinds of lasers like solid state lasers or some gas based lasers or something, typically you want to have these mirrors very good, right? Like 95% or 99% reflectivity. But here with semiconductor lasers, because the gain is so large, even with such low reflectivity mirrors, one can actually have laser. Right. So again, if we look at what is happening right here between, so in this laser cavity. So if we start from one end here, right? So let's say the field is E naught, okay, and then we see basically what happens in one round trip. Okay. So we do one round trip and come back. So here E after one round trip. So let me call that one round trip. Right. So what all is happening to the field, right? So of course there is this gain happening, right? So depending on the carry concentration here, so there is some e to the so g by 2, and then z here, the propagation distance for one round trip is 2L, right? So L and then L. So g by 2 times 2L. So the gain coefficient for the electric field is g by 2, and then times 2. So you basically get e to the gl, right? And then we include another factor here actually. So capital gamma along with g times L, right? And that gamma is basically telling me the confinement factor of the mode here. Okay? So basically, the light emission and the amplification is happening only in this active region here. But you can see that the mode is extending out into the PN regions. So just like for a mode in an optical fiber, for example, you can calculate what is the fraction of power which is within the active region, right? So only that fraction of power is experiencing the gain and not the rest of it, right? So to take that into account, there is this confinement factor capital gamma. And typically this is actually quite small. So this gamma typically is less than 40%. Okay, so the mode is actually leaking out from the active region quite a bit. And the reason for that is firstly, again, as we discussed, this active region is quite thin, right? So let's say 100, 200 nanometers. And also the index contrast between the active region and the PN region is very small, not much, right? So the band gap, we change it by, let's say, 0.1 or 0.2 EV. So the refractive index contrast between these is not much at all, right? Maybe 0.01 or 0.02 or something like that, right? So, so for example, if you calculate an equivalent V number for this, that V number is quite small, right? Which means the confinement factor is very low. Like the mode is leaking out quite a bit. Okay, so this confinement factor typically is less than 40% for a typical, so it could be like 10, 20, 30%. Okay, so that's the gain part. Okay, and then we have some internal losses happening. So we can take a loss coefficient alpha internal here, same thing like for the gain. So if you want to model the loss, we just have a minus alpha here instead of G. Right, so we take that alpha internal. So that is again because of, let's say, some scattering which is going on here. Let's say because there are some defects, so some internal absorptions going on here, some scattering. Okay, so all this because this device inside here is not totally perfect. Okay, so the loss is happening internally. So typically, if you take a commercial semiconductor laser, this internal loss coefficient alpha internal typically is in the tens per centimeter, like for example 20 per centimeter or something like that. So it's in here. So you can see that we can easily exceed this. So G can easily exceed this alpha internal for reasonable one, especially once we go beyond transparency. Okay, so that can happen. Then what else is happening? Of course, we are losing some light at the reflections here, right? Because these are not 100% reflecting. So for the field, you know that so if the power reflection coefficient is R, then the field reflection coefficient is square root of R, right? So there is square root of R2 reflection happening here, and then square root of R1 times the field gets reflected here. So if I multiply both of them, so I get square root of R1, R2 here. Right. So we are taking R1 and R2 in general could be different. They could also be the same. Right. So for example, if you just have 3 facets, then they are the same. But for example, you could have a different coating here as compared to here. Especially, for example, so for a device like this, typically light will come out of both facets, right? But let's say if you want light to come out only out of one facet, then you make one of them very highly reflecting, right? So you coat here so that this becomes like 99%. So then basically all your light just comes out of one facet. Right, so this is happening. Then one more thing is happening, right? So of course you know, so this electric field is a complex number, right? It has an amplitude and a phase, right? So this is happening to the amplitude, you can see, but of course the field is also acquiring a phase shift on propagation, right? So again, if you consider this as some mode, it has a propagation constant, right? E to the I beta z is the phase acquired. So it also acquires a phase here. So again, that's I beta z, where z is 2L. Right? Beta is the propagation constant for this mode that is formed here. Okay, and in steady state, basically in the lasing condition, what we want is that now all this is balancing out, and then after the round trip, the field basically comes back to the same value, right? So we reach steady state means that the field is not evolving anymore, right? So basically, after all these effects, the field is remaining the same from what it started. Okay, so basically you can see all these factors being multiplied, all of them should combine to give you 1. Okay, so now we have like a real part here and also like a complex part here. So in the exponent we have a real part and an imaginary part. So for it to be 1, right, the real part has to be 0, right, and the imaginary part has to be some multiple of 2 pi. Right, so if this is some m times 2 pi, then you know that this is just 1. So we get 2 conditions. So one is for the amplitude here. So we take the log of this to take these factors from the exponent to the down from the exponent. So you see that. So we get a condition on the gain. Okay. So when we take the log, of course, these factors in front of each just come out, and then for this square root of 1 by r1 r2, we get log of r1 r2, and then half here for the square root, and then L comes from both these factors. So we divide by L, so we get. Okay, so this is the threshold condition for lasing. Right, so these are, so once you make the device, then this internal loss coefficient and the reflectivity of the mirrors and the length of the device, that is all set, right? That is a property of my device. And now this G depends on the carrier concentration, which depends on the injected current, right? So to find out where, at what injected current will I start lasing, that is given by this equation. So once the gain becomes equal to this value determined by the losses of my device, then at that point I'll go into lasing, and beyond that current I'll be in the lasing region. Okay, so that's one condition, and then the other, there is also a phase condition here, right? So that is 2 beta L, that's the phase, has to be some integer multiple of 2 pi. So this is the integer. And to be more specific, it has to be positive integer. These are positive values here, so this is some positive integer. Okay, so if you write beta, remember, so we can write beta as omega over c times n effective, right? Where n effective is the effective index of the mode here, right? Or roughly, it's basically just the index of the medium. Right, and omega, of course, you know, is 2 pi times the frequency in hertz. So if you equate this condition here, so you can see that whenever the frequency nu is a multiple of this value c over 2 times refractor index times length, right? At those frequencies, this condition is satisfied. Right, so this tells me that, so for example, here I have like this whole range of frequencies for which I am getting gain, right? So you can imagine that at some particular current, I can satisfy this equation for some particular range of frequencies, but not all of them will lase, right? Because not all of them satisfy the phase condition. Only some discrete values, right? So only some discrete values within here will satisfy this phase condition, and only those frequencies can lase. Okay, so this is again unlike now an LED, so where we had a continuous output, right? A continuous spectrum of frequencies. But for a laser, you can see now you can only have a discrete set of frequencies. Okay, so basically this G depends, as we saw, so it depends on the carrier concentration, which depends on the current, right? So basically from this G threshold, we can get an I threshold. So typically this G is related to the current, or the current, more specifically current density J, right? So J, recall, is I divided by W times L. So you take out the cross section of the device. So this is ampere per centimeter cube. Okay. Yeah. So basically, the carrier concentration directly depends on I or J, and then since G depends on N, so you can find that some proportionality constant between J and this one. Okay, so this proportionality constant you will see in some places it's denoted as B dash or B bar to differentiate it from this beta propagation constant here. Right, so this beta bar is known as the gain factor of the laser. Okay, and it has units of length per current, centimeter per ampere, because again G has units of per centimeter. This is amps per centimeter square, right? So you can see this is centimeter per amp, right? So again, this depends on sort of my material and doping, etc. So higher the value of this beta bar, I can achieve threshold at a lower current, right? Or the device is more efficient. Right. So if you look at this phase condition here, so again, what we talked about is, so we have this continuous gain bandwidth, but within that only discrete frequencies are satisfying this phase condition. So, for example, if I look versus frequency nu, so at some particular current, I'll have some gain profile. Right? Basically, we draw those, do those different sets of G for different n values, which are basically different current. Okay, so let's say at some particular operating current, I have some. This is the shape of the gain with frequency, right? So I have peak gain at some particular frequency, and so let's say there is some. So the right hand side here is giving me the total loss of my device, right? Coming from the internal losses and the mirrors, right? So you can see this right hand side is sort of frequency independent, right? So this left hand side is of course dependent on frequency, as we just saw, but the right hand side is sort of frequency independent. I mean, in general, it could also be frequency dependent, but typically over the range of wavelengths we are looking at, right, just over the gain bandwidth of the laser, typically the loss coefficient is frequency independent, and these mirror reflectivities are also not dependent on the frequency. Okay, so the right hand side is sort of a constant with respect to frequency, so that is some value here, right? So this is gamma times G, so the gain factor normalized with the confinement factor, and this is the loss, alpha internal plus mirror reflectivity. Okay, so and this of course now is depending on the current. So as I increase my current, this shifts up and up, right? At some point, the peak of this gain curve touches the loss, right? So basically at this point, for this particular frequency, right, I've achieved this condition, gain equal to loss, right? So this is some particular mu naught, right? And if this mu naught also now satisfies this phase condition, then basically you'll start lasing at this frequency. So now, if I increase the current further, then now you can see that basically now this gain curve goes like this. So it will exceed the loss for a certain range of frequencies. Okay. But what happens is actually we'll see that once you go beyond threshold, it's not that G keeps increasing linearly with the kinetic concentration or the current. So that's true up to threshold. Once you go beyond threshold, what happens is that the gain actually gets clamped. Okay, so here the gain gets clamped at the loss value. So we'll see that in more detail how that happens. Okay, so this is known as gain clamping. So I mean, you can see that this has to happen. Why? Because so if the gain remained higher than the loss, then you can see from here, right? Then basically now the field will acquire exponential gain, right? If now the gain exceeds the loss, then it will keep amplifying, and the field will run away to infinity. Of course, that's physically not possible. Right? So what happens is actually once you reach threshold, even further increase in the current beyond threshold doesn't increase your gain further. Okay, so the gain actually gets clamped. So now you can see for some particular current above the threshold, there's a range of frequencies here for which the gain is equal to the loss, right? But not all these frequencies will lace. Okay? So again, we come back to the phase condition. So there will be some discrete set of frequencies here. Okay, so these are for different n values. So the spacing between this you can see is C over 2 NL. That's known as the free spectral range of the laser cavity. Right. So basically, this is a Fabry-Perot cavity with different modes. Right. These are different longitudinal modes of the Fabry-Perot cavity, and the free spectral range is inversely proportional to the length of the cavity. Right. So if this is longer, then the modes are more closely spaced. Right. So basically, within this region here, you can see only these modes, the ones which satisfy the phase condition, they will lace. Okay, not the whole continuous set of frequencies, but only these. Okay, so you can see that the lowest threshold is for the frequency which is closest to the gain peak, right? So that frequency will achieve this gain equal to loss condition at the lowest current, right? And then as you keep increasing current, then you start bringing other frequencies into the picture. Okay, so there is a subtlety here that so you know that this n is also a function of frequency or a wavelength. Right? So if, for example, even if you just take the material refractive index, then the material refractive index actually depends on frequency, right? So this is not this n is not independent of frequency or wavelength. So right, so this n actually also depends on frequency or wavelength. Okay, so you can see that then the spacing is if you include this frequency dependence of the refractive index also, right, then you have to calculate the FSR as a successive difference between successive frequencies. Okay, and then basically this will be m times c over 2 times n at nu m, right, and this will be m minus 1 c 2 n at nu m minus 1 times l. Okay, so I can't just take, I mean, if I assume if I don't neglect the frequency dependence of the refractive index, then this n, these two n's are not the same, right? And then you can see that the FSR won't come out to be this, right? So you can do some, you can do the math here and make some approximation that the difference here between successive, the frequency difference between, or the refractive index difference between these two adjacent modes is very small compared to the absolute refractive index, and you can do a Taylor expansion of the refractive index, right, about nu m to find nu m minus 1. So you can see that when you do that, you'll have a term something like so nu m minus 1 will be something like nu m minus so this FSR difference in frequency here times dn by d nu, right? So this looks something like the group index, right? We call the group refractive index is the bare refractive index plus this term dn by d omega. Right? So if you do that, basically if you include this frequency dependence, this n actually becomes the group index. Okay. So to be more precise, the FSR is actually given by the C over 2 Ng, the group index times that. The difference is not much, but in certain cases, it might prove to be not negligible. Okay. Like for these cases, for example, they're not very much different. Like the absolute index would be, let's say, 3.4, and the group index would be 3.5, not more than that. Okay, so the difference is quite small, but to be precise, this is the group index. Okay, so you can try to do this at home and see you get this group index. So there's a question: what is FSR? FSR is what I'm talking about. Difference between adjacent, the frequency difference between the adjacent nodes. Right. New one. It's called free spectral range. Okay, so if I look at typical laser cavity, so how many modes, how many frequency modes are coming from a laser depends on this free spectral range in comparison to the gain band, right? So, so if you take a typical laser cavity, semiconductor laser cavity, so length, let's say 200, 400 microns, then this FSR comes out to be about 100 to 200 gigahertz. Or in delta lambda, okay, so if this is a FSR in frequency, so if I call it delta nu FSR, then the relation between delta nu and delta lambda, you can see this is just will be lambda square over 2 ngl. Right, I just multiply this by lambda square over c. So this comes out to be about 1 or 2 nanometer. Right, so let's say if I take the wavelength around 1.5 micron. So if I put lambda equal to 1.55 for these length values, Ng again is, let's say, 3.4 or 3.5. The this FSR comes out to be about 1 or 2 nanometers here. Okay, so that's sort of roughly the scale we are talking about. Okay, so this is the regime where so-called laser diodes operate. Okay, so laser diodes are basically these semiconductor PN junctions with an active region, cleaved facets, maybe one polished facet, right, and that's about it. So with such a device, basically what happens is, so once you operate, let's say, above threshold, right, if your current is about twice or thrice the threshold current, then you have a situation like this, where like multiple modes are lasing. So if you look at the spectrum of the laser for a laser diode, so it is what is known as a multi-mode spectrum, right? So if I look at the spectrum coming out, so it will have some envelope, but of course the frequency components are discrete, right? So unlike an LED, right, so where the spectrum was continuous, all the wavelengths were present. So here only discrete wavelengths are present, okay, but there are multiple of them. Okay. So like for these laser diodes, typical, so this gain bandwidth typically, let's say, could be anywhere between 2 to 10 nanometer, right? Again, it depends on the doping, the material used, and the current they're operating at. Right? That gives you this gain bandwidth, right? And then, so how many modes fit within that gain bandwidth depends on now again the FSR, right? So typically you have, so if your FSR is like a nanometer or so, then typically you have, let's say, if you have 10 nanometer bandwidth, you'll have, so here you'll have like maybe 2 to 10 lines. Okay, so basically a laser diode has what is known as a multi-mode spectrum. Right, so it's not a single frequency to be precise. It's like a collection of frequencies, maybe 5 or 10 lines, different frequency closely spaced, coming up. Okay, so I mean, so these are already a very big improvement over LEDs, right? But we saw that the performance of the communication system could still be limited for these sort of source bandwidths, right? And so what is done is that you can now eliminate. So what you want to do finally is have only one of these. Instead of having multiple frequencies, you only have one particular frequency coming up, right? That is your ideal laser. So how do you eliminate these different modes, right? So what is happening, why these are happening is that once you go above threshold, basically your gain equal to loss is satisfied now by a whole range of wavelengths, right? And basically the lines or the longitudinal modes falling within this bandwidth are all laid. So we have to somehow ensure that only one of these lays and all the rest don't. Okay? And the only way to do that, you can see, is somehow to make the gain equal to loss condition be satisfied only for one of the frequencies and not the rest. Okay? So we have to do some trick for that. So you can see that cannot happen if you have a flat frequency independent loss profile like this. Of course, that cannot happen, right? So as soon as your gain profile starts exceeding the loss, then you'll have a range of multiple different modes which will satisfy this. So the way to make what are known as single frequency or single longitudinal mode lasers, right? So these different frequencies are known as longitudinal modes. So for a single frequency laser or a single longitudinal mode laser, basically you have to play with the loss profile and somehow make the loss profile also frequency dependent. Okay, so again, if we go back to this picture, okay, so now instead of a flat loss profile, let's say the loss drops for around a very narrow range of wavelengths or frequencies. So let's say somehow you are able to engineer the loss in the device such that the loss is smaller for a very small range of frequency or wavelengths. Okay. So now again, go back to your gain profile here, right? So as I keep increasing the current, so this goes up, right? At some point, you'll see that this will touch here, right? So this gain equal to loss condition will be first satisfied for this point of minimum loss. So for this particular, so let's say now if I plot my modes, they are like that, right? So these are different M, and this is the FSR. Right, so this particular mode, which is closest to the minimum loss point here, so that will achieve this threshold condition at the lowest current. Right, and now if I increase it further, you can see that because of this loss profile here, right, actually there is still some room for other like at other frequencies and wavelengths, there is still some gap between the gain and loss. Okay, so I could increase my current further. Okay, so you can see that it will still, the gain equal to loss will still be satisfied only for frequencies very close to this minimum loss point. And so if that is narrower than sort of your FSR, then you can see that only still this mode will be lazy, right? So for this mode, your still loss is above gain. This mode also loss is above gain. Okay, so you can see that with such a frequency dependent loss profile, where the loss sort of goes down for a very narrow range of frequencies, you can achieve this. So in this case, the spectrum coming out will just have this particular frequency mu naught. Right. Of course, this won't be a perfect delta function again. There will be some line width here. So we'll see what this line width will be limited by. But again, of course, this is still much better than having multiple lines, right? So this delta nu will depend on some factors that we see, but this can be made as small as, let's say, few kilohertz. Okay, so the best semiconductor lasers have line width of few kilohertz, maybe 10 kilohertz. Okay, and the absolute frequency, of course, we know it's like whatever 200 terahertz. Right? So this is how we make single frequency or a single longitudinal mode lasers. Okay, so how to get this kind of loss profile, we'll see in a minute. But let's just discuss some general metrics for the laser. Okay, so what one is interested in is, so typically you want output at some particular frequency, right? And your output spectrum might have some other spurious frequencies. Let's say then this is the next mode, for example. Okay, so there is also some power output at that, but you don't want that, right? You want only this particular laser. So basically, you want to look at the suppression of this with respect to this, right? So if this is the power in the main mode, and this is the power in the side mode, right? So you want to look at this ratio of the side mode divided by the main mode. Okay. So typically, you look at this in dB. Okay, so this is known as sideband suppression ratio. Okay, so for good lasers, you want this typically at least 30 dB or more, right? Which means the power in the main mode is like 1,000 times higher than power in the side mode. So that then well approximates to a sort of single frequency laser. So there is one question on explaining the operation of this beyond the threshold. Is that, yeah, so I mean the main point is that because of this sharp feature here, right? So the threshold is when the gain just touches here, right? And then as you increase the current further, you can see that because away from this minimum loss point at which the threshold is happening, the loss is also going up, right? And so there is some gap here between the gain and the loss. So if I increase the current, the gain goes up, but the loss has also gone up here at frequencies away from the minimum. So I'm still below the threshold condition for these frequencies. Similarly on this side. For the flat loss case, basically what happened was once I reached threshold for this point where the maximum gain was, Now if I increase further, right, basically all these frequencies nearby will also now satisfy the threshold condition, because the loss for all those frequencies are the same, right? So there is no room for me that right, like as soon as I increase the current, the frequencies for which the threshold condition satisfies keeps increasing, because more and more frequencies satisfy the loss. Whereas here, because right, so there's a big gap here, so I can increase the current further without reaching the threshold condition for these side modes. So that's the that's how you avoid multi-mode lasing, and you go to just single mode. There's another question of how to observe the modulation bandwidth of semiconductor laser diode. That we'll study maybe in the next class, right? So the modulation characteristics. So if I just like we discussed for an LED, right? If I modulate the current, my optical power output also will be modulated, and I can use that to encode electronic data onto the optical wave, right? Similarly, you can do with laser also, of course. Right. So first we'll study the steady state or DC characteristics of optical power versus injected current, and then we look at the AC characteristics of the modulation characteristics. So if you vary the current, how does the power output, and what is the bandwidth decided by, etc. That we'll look at in the next class. Yeah. Okay. So yeah, for a good laser, basically you want the sideband suppression ratio to be more than 30 dB. So state-of-the-art lasers, single frequency semiconductor lasers, if you look at nowadays, this suppression ratio is like more than 60 dB. Okay, so it's truly single mode. Any other spurious modes are way down, right? A million times lower at least. So coming back to this point of how to get this frequency dependent loss profile, right? So recall, so the loss is determined by the internal loss mechanisms like scattering and absorption in defects, etc., and then the mirrors, right? So it's hard to control the internal loss factors, right? That sort of is just decided by how good your fabrication is, and also you can't really imagine how to make that frequency dependent. But of course, mirrors, you know, right? We can make mirrors by these. I mean, for example, a popular way to make mirrors is this multi-layer coatings, right? And depending on the period of these coatings, that decides the wavelengths which are reflected. And you know about the concept of Bragg reflection already, right? So, for example, fiber Bragg ratings, you vary the refractive index periodically, and that reflects a particular wavelength or a very narrow bandwidth around a particular wavelength, right? So, if you could make, using this concept, frequency dependent mirrors, basically, right, that have high reflectivity for a particular narrow bandwidth of wavelength or frequency, right, and then low reflectivity away from that. So just like, for example, if you have a Bragg rating, right, it has high reflectivity, so the loss is inversely proportional to the reflectivity, right? Higher the reflectivity, the lower the loss, right? So you can see that basically you want high reflectivity here and low reflectivity here. So that's just like looks like the reflection spectrum for a Bragg rating, for example. Right? So what one can do is have a Bragg rating, have a Bragg rating act as a mirror. Okay, so there are two types of ways to do this. So one is known as a DBR laser. So what you do is, again, I'm looking at this laser from the side. So this is length L. Okay. So so this is the active region. This is the N region. And now, so let's say you have a P region. So what you do is, after some point, you have some sort of Bragg structure here. So periodic variation is sort of, so if you imagine some mode propagating like this, right? So let's say you have a region of some P plus, a different amount of doping here, right? So the refractive index will change slightly. Right, so just in phylo Bragg gratings, we write the grating using UV light, right? What we do is we physically make the structure of different heights, right? So you can see that the effective index seen by the mode will be different here than here, right? So it looks like a grating for this mode. Okay, so there's a Bragg grating here, there's a Bragg grating here. So these are my two mirrors. Okay. And then the wavelength which is reflected most efficiently will depend again on this periodicity here, right? The periodicity of this Bragg structure, right? So by having a particular period here, I can ensure the high reflectivity or the low loss at that particular wavelength given by the Bragg conditions, right? Okay, so this is known as a DBR laser, or distributed Bragg reflector. Okay, so right. So instead of just having the facets act as mirrors, you have some Bragg gratings to act as mirrors. So the point of the Bragg grating is that you know that the reflectivity spectrum for a Bragg grating is very narrow, peaked at this Bragg wavelength, which depends on the periodicity. So basically, we have this minimum loss corresponding to this wavelength, lambda b. Okay. So only that particular wavelength will place. Okay, an easier structure to make sort of is to have this distributed reflection all over the laser cavity itself, right? So you can have something like this. Okay, so basically have this Bragg region over the entire cavity length itself. So, I mean, why have mirrors at the end? So this way your device also has to be longer, right? You can just distribute the reflection over the cavity length itself. Okay, so this is known as DFB, or distributed feedback. DFB laser. Okay, so with DFB you can make more compact cavities, right? And making the cavity compact, you know, also the FSR, right, scales inversely with length. So a smaller length means that the frequency separation is higher now. So you go away from this even further. So that gives you a better sideband suppression and closer to a single frequency. Right. So from the grating period here, you can from this Bragg condition. So for example, if I want a 1.55 micron laser, you can see. So for n again, like 3.4 or something, this periodicity has to be about 250 nanometer. Okay, which you can easily make with semiconductor lithography techniques. Which are used for semiconductor nanofabrication. You can use those techniques to make these features. Okay, so that's so this is one way, DBR or DFB, and this is like within done at the time of making the semiconductor device itself. It's on the chip itself, so this is more compact. There is another way which is known as external cavity. So if you don't want to make these, so you can imagine that making these Bragg structures, of course, increases your internal losses a little bit, right? Because you have to do this extra processing. So that increases your internal losses and increases the threshold a little bit. Okay. So if you want not to touch your laser cavity but somehow still make it single mode, then what you do is go to an external cavity. So it's known as an external cavity diode laser. Right. So what you do is you have your semiconductor laser, and then you put it inside an external free space cavity. Okay. So and so you have a laser cavity of length L inside a bigger cavity of length L prime. Okay, so now your mode has to travel both within the laser cavity and then within this external cavity also. Okay, and then let's say you have one of the mirrors of this external cavity on a movable stage. So you can move this mirror. So you can change L prime. Okay, so you can imagine, so this external cavity will have its own FSR, right? So this external cavity is like a ferro cavity on its own. So it has an FSR which is much smaller than the FSR of the laser cavity here. Right? Again, FSR is inversely proportional to length. So right, so basically you have these modes for the external cavity, okay, where the FSR is small. So you see delta FSR prime is proportional to 1 over L prime. And then you have this internal cavity within the laser here, which has an FSR much bigger, right? So this is for the internal cavity. So this delta nu FSR is proportional to 1 over L. And you can see that the modes which will laze is the ones which satisfy both these conditions simultaneously, right? So this mode, let's say, satisfies the round trip condition for the external cavity and the internal cavity. Okay, so these two line up. So this mode can laze, but this next mode for the external cavity does not satisfy the round trip for the laser cavity. Okay, so that cannot laze. And if you ensure that basically these are not some multiple of this, then the next mode which will line up for this will be very far away. Okay, let's say outside your gain bandwidth. Right, so by this external cavity, you can ensure that only one particular mode lasers. Okay, so that's another way of making single frequency laser is the external cavity. And now this gives you an extra flexibility is that by moving this mirror here, you can change L prime, which means you can change these frequencies slightly, right? So let's say you move this a little bit. Now what happens? All these shift a little bit. And now this particular mode lines up. Okay, so now this doesn't line up anymore. So they've shifted a little bit. If the shift is just enough that this next mode now lines up with the external cavity mode, so now this will laze. Right? So by controlling the position, you can tune the emission. So this is not only the single frequency laser, it can also be tunable. Right? These are fixed because once you've made a grating of a particular period, then the wavelength of emission is fixed. You can't tune it. Right? But with the external cavity, you can actually tune the emission wavelength. Okay, and with these ECDLs, you can have very widely tunable lasers spanning, like let's say 100 nanometers from 1400 to 1500 or 1500 to 1600. Okay, and so you can set a wavelength anywhere in between that, and it will give you a single frequency, and you can change the frequency of emission or the wavelength of emission very precisely by. Okay, yeah, so. This is a little bit more mechanically complicated, right? Because you have to have stabilize this external cavity around this internal cavity, but it gives you this extra freedom of having the laser tunable. So, let's say you want to change the wavelength for some particular application, then you can do that.